Chemistry time.
Hello everyone! Today we are going to begin this chapter by first delving into the periodic table. First things first, when we refer to a column on the periodic table, this is referred to as a group, and a row is known as a period. Up until this point, you have been using this table on exams, homework assignments, and during lectures. But have you ever wondered how it came to be, or even better, who helped create it? Well, a number of people have contributed to its creation, such as in the 1820s, German chemist Johann Dobereiner helped with the development of the periodic table by grouping elements into triads, which simply means three elements that are chemically similar. Roughly 50 years later, John Newlands, who was an English chemist, observed a trend in the periodic table that if elements were arranged by increasing atomic weights, he noted a periodic trend that every eighth element fell into a group that had chemically similar properties. This was known as the law of octaves. The father of the periodic table is primarily credited to Dmitri Mendeleev, who arranged the elements in the modern version of the table. His table followed periodic law, which simply means that a new row was started when elemental characteristics began to repeat themselves. By arranging the elements in this fashion, he was able to predict undiscovered elements, and he could also disregard accepted atomic weights if their periodic properties did not match the group they were in. So you must be wondering, how does the periodic table refer to quantum mechanics? Well, so far we have mentioned that on the periodic table, elements that fall in the same group have similar properties. Do you know why this is the case? Well, this is all attributed to the electrons in the atoms, and this is going to explain a number of phenomena. So far, we have learned about quantum numbers. Remember N, L, ML, and MS? Well, we will be using these numbers to write electron configurations, which is a notation that is used to show which orbitals electrons are occupying. So when we say orbitals, we are referring to the s, p, d, and f orbitals. To begin, let's refresh on a few things, such as how do we know how many electrons are in an atom? Well, if we look at the periodic table, we know the atomic number tells us the number of protons in our atoms. So let's use hydrogen for an example. It has an atomic number of 1. In order for this atom to be neutral, it must have an equal number of protons and electrons. So if hydrogen has 1 proton, it must also have 1 electron to be neutral. So now that we know how to determine the number of electrons in an atom, we can begin to represent elements by writing out the electron configuration. When writing out an electron configuration, you first start by writing the energy level, which, if we remember from previous lessons, this is the principal quantum number, which is denoted by N. The energy level is determined by the period that the element is located in. If you count down the periodic table numerically, so starting with hydrogen, this is N is equal to 1. The next period is N is equal to 2. The one after is N is equal to 3, and so forth. The next component you write is the orbital. So this is referring to S, P, D, or F, and followed by the number of electrons in that orbital. We will use orbital diagrams to help us visualize this, and we will denote orbitals as boxes, and electrons will be denoted as half arrows. When an arrow is pointing up, this will be denoted by positive 1/2 spin, and an arrow pointing down will be denoted by negative 1/2 spin. So let's start by writing the electron configuration for hydrogen. It is in the first period, so N is equal to 1. We know when N is equal to 1, we have an s orbital, and we know we have 1 electron in the hydrogen atom. So the electron configuration is 1s1. Perfect, let's continue on, and let's do the same for helium. But before we can write the electron configuration, we must first introduce the Pauli exclusion principle, which states that no 2 electrons can have the same 4 quantum numbers. So what this means, we can have the same value for N, L, and ML, but the 4th quantum number spin must be different. This is why when we write the orbital diagrams, we have half arrows pointing up and pointing down. Okay, so let's continue with writing the electron configurations for helium. Well, helium is also in the first period, so N is equal to 1 and has 2 electrons to distribute. So the electron configuration is 1s2. Please remember to abide by the Pauli exclusion principle when filling in electron configurations. As we continue to write these electron configurations, we will begin to run into an issue of which energy levels or orbitals do we fill first. while the Aufbau principle states electrons are added to the lowest energy orbitals first before filling higher energy orbitals. So we are essentially building up the electron configuration. For lithium, it is on the second energy level, so n is equal to 2. When n is equal to 2, L is equal to 0 and 1, which means we have the s and p orbitals available. And lithium has 3 electrons to distribute. Let's go ahead and distribute these electrons, and remember to always include the lower energy levels. So we first fill in the 1s orbital, which can accommodate 2 electrons. We still have 1 electron to distribute, so that will be filled into the 2s orbital. So the final electron configuration is 1s2, 2s1. So now that we have the hang of this, let's continue doing the entire second period. Beryllium has 4 electrons, so we build it up and it will be 1s2, 2s2. Boron has 5 electrons, and we will first fill in the 1s2 orbital, followed by the 2s2. We still have 1 electron to distribute, and this will go in the 2p orbital. So the final electron configuration will be 1s2, 2s2, 2p1. Another concept that is important to know before we continue is Hund's rule, which states that every orbital in a subshell is singly occupied with 1 electron before any electrons are paired. When filling these orbitals, it is important to maximize spin, which simply means unpaired electrons have the same spin. By doing so, we are forming the most stable arrangement. We can apply this rule when we write out carbon's electron configuration. So it has 6 electrons to distribute, so 1s2, 2s2, and now 2p2. But remembering to place the electrons in their own separate orbitals in order to form the most stable arrangement. By placing them separately, this reduces the electron-electron repulsion, thus stabilizing the atom. So I'm going to go through the next few atoms a little quicker because at this point we should be getting the hang of writing these out. So nitrogen will be 1s2, 2s2, 2p3. Oxygen will be 1s2, 2s2, 2p4, making sure to now pair the electrons because there are no more empty orbitals. Fluorine is 1s2, 2s2, 2p5, and finally neon is 1s2, 2s2, 2p6, which it is important to note that neon and helium, when you write the electron configurations, have no empty orbitals, which this is why noble gases are extremely stable. So right now you are able to write the electron configuration for the first 3 periods on the periodic table. Next lesson we will go over how to write the electron configurations for the next section of the periodic table. Thank you for tuning in to Chemist Tea Time. Have a wonderful evening.